When we think of a computer today, we think of something that fits on our desk, in our lap, or even in the palm of our hand. But it wasn't always this way. The story of how we got from machines that filled entire rooms to the devices we use every day is a fascinating journey of incredible transformation. We're going to trace the key technological leaps that made it all possible.
Let's start with a number 30 tons. That's what? The weight of a few school buses? Maybe a whale? Just try to picture that kind of mass. Now imagine it's all for a single machine.
Because that was the reality back in 1946. That 30-ton machine was the ENIAC, the world's first general-purpose electronic computer. And really, it's the perfect place to start our story. A true technological giant that set the stage for this relentless march toward making things smaller, faster, and more powerful.
You see, the ENIAC was part of very first generation of computers. And this whole era, it was defined by one single, crucial, and, as it turns out, very problematic piece of technology, the vacuum tube.
To really get a sense of the challenges they were up against, you just have to look at the ENIAC's stats. We're talking about over 18,000 vacuum tubes. Every single one of them was a potential point of failure, and they failed all the time. The machine took up the space of a small house and sucked out enough power to light up a whole neighborhood. And get this, you didn't program it by typing code. No, programming was a physical job. You were literally plugging and unplugging thick cables and flipping thousands of switches by hand.
So the path away from these huge, unreliable machines can really be mapped out across 3 distinct generations. Each one was kicked off by a major breakthrough in hardware. We're going to follow that path from the vacuum tube to the invention of the transistor, and then finally to the integrated circuit.
But here's what's so interesting. Even while engineers were wrestling with these massive physical problems, tubes burning out, insane power consumption, a really powerful and lasting idea about the design of a computer was taking shape. The mathematician John von Neumann, who was a consultant for the ENIAC project, he came up with a logical structure, a kind of blueprint that was so good it would outlast all of this early hardware. And this blueprint, which we now call the von Neumann architecture, was beautifully simple. It broke a computer down into 4 key parts. You've got a main memory, and this is crucial. It holds both the data and the program instructions. Then there's an arithmetic and logic unit, or ALU, that does all the number crunching. A control unit acts like a traffic cop, fetching instructions from memory and executing them. And finally, you have your input and output gear to talk to the machine. It's an elegant design, and it's still the basic model for almost every computer we use today. So the big problem with the vacuum tube was its size, the heat it generated, and just how fragile it was. Well, the solution showed up in 1947, out of Bell Labs. It was a solid-state device, and it didn't just solve the problem. It kicked off a revolution that defined the entire second generation of computing. This new invention was the transistor, and compared to the vacuum tube, it was just better. In every single way. It was tiny, it was cheap, and it barely generated any heat. It was made of solid silicone, not delicate glass, which made it unbelievably reliable. This one invention, right here, it changed absolutely everything. And it didn't take long for the impact to be felt. By the late 1950s, you could buy computers that were fully transistorized. And they were fast. On average, about 5 times faster than the old vacuum tube machines, capable of cranking out around 200,000 operations every second. But this wasn't just about making things faster or smaller. Because transistors were so reliable, engineers could build much more complex logic units. It also made things like high-level programming languages and system software, the beginnings of operating systems, possible. You started to see really sophisticated machines like the IBM 7094 that had advanced features like dedicated channels just to handle input and output, which freed up the main processor to do the heavy lifting. So as these new transistor-based computers got more and more powerful, they also got way more complex, and this created a whole new problem. Suddenly, manufacturers were facing the enormous difficulty of wiring together hundreds of thousands of individual, separate components. Think about it. Every single transistor, every resistor, every capacitor had to be made one by one, put in its own little package, and then carefully soldered onto a circuit board by hand. It was an incredibly slow and expensive process. This was the next big wall that computer progress had run into. And the solution, which came along in 1958, was just brilliant. It was the integrated circuit. The idea was a total game changer. What if, instead of assembling all these separate parts,
You could build an entire circuit, the transistors, the resistors, and all the wires connecting them, all at once, on one single tiny chip of silicon. This single invention launched the era of microelectronics, and it led to one of the most powerful and predictive observations in the history of technology. In 1965, Gordon Moore, who would later co-found Intel, noticed something. He saw that the number of transistors you could cram onto a single chip was doubling at this incredibly predictable exponential rate. This became known as Moore's Law.
To really feel the power of that exponential growth, you just have to look at the numbers. So in 1971, a very early microprocessor had about 2,300 transistors.
Okay, now jump forward to 1989, not even 2 decades later. That number had exploded to over 1.2 million transistors on a single chip. And by 2011, a processor could have over 1.17 billion transistors. It's just this relentless, predictable, exponential progress that completely reshaped the entire industry. The effects of this were just profound. The cost of computing basically went through the floor. Because all the parts were so close together, the electrical signals had less distance to travel, which meant speeds went way up. Computers got smaller, they used less power, and they became way more reliable because you were replacing all those fragile solder points with tiny, perfect pathways etched right into the silicon. And the integrated circuit didn't just make existing computers better, it opened the door to entirely new ways of thinking about how you could build and even sell computers. For a perfect example, look at what IBM did in 1964 with its System/360. This was the first planned family of computers. You had different models, from the basic Model 30 all the way up to the super powerful Model 75. But here was the genius part. They were all software compatible. A program you wrote for the small machine would run on the big one. This meant businesses could upgrade their hardware as they grew without having to throw out all their expensive software. It was a huge deal. And then, just a year later, another revolution happened. The DEC PDP-8 came out. It got the nickname mini computer because it was small enough to fit on a lab bench. And at about $16,000, it was affordable enough that you no longer needed to be a giant corporation to own a computer. This created a whole new market outside of those giant air-conditioned data centers. And finally, in 1971, this whole journey of miniaturization reached its ultimate goal. Intel managed to put all the essential parts of a central processing unit, a CPU, onto a single tiny chip of silicon. The microprocessor was born, and that is the invention that directly led to the personal computers, the smartphones, and all the devices that have completely defined the world we live in today. So for half a century, one simple observation, Moore's Law, has been the engine driving this entire digital revolution forward. But now, as we start to bump up against the actual physical limits of silicon, that pace is finally starting to slow down. And that leaves us with a big, critical question for the next era of computing. What happens when that engine of exponential progress finally runs out of road?